Okay, Frobenius method. So Frobenius method. This method is used, Frobenius method. This method is used for those equations which do not have any uh, uh, analytic points. So what I mean by the analytic points is that, for example, if you take an equation, so for example, y double prime plus bx over x and plus that is y prime plus any other equation. So I'm cx over x square y is equal to 0. So this, for example, if we have this equation, I mean, in standard, in other form, you will multiply this by x square, so it will be x square y prime plus bxx, that's y prime, and then cx. So in this equation, these functions bx and cx are defined at the value of x is equal to 0. So for example, this equation, so for example, y prime minus y is equal to 0. So this is the first order equation. So in this case, the coefficient of this y, which is over here as cx, is 1. So 1 is a defined function for any value of x. Similarly, so this therefore the function over here is analytic. And also as another example, we have 1 minus x square y double prime minus 2xy prime plus 2y is equal to 0. So this is also another equation. In this case, if we take its standard form in which we start from y double prime, so then y minus x, 1 minus x square over here will be in the denominator. So it will be y double prime minus 2x over 1 minus x square plus 2 over 1 minus x square, and that is y prime, and that is y is equal to 0. So in this case, these coefficients of y prime in the form of these functions and y, they both are analytic, which means that at x is equal to 0, these functions exist. So for example, at x is equal to 0, this is 0. So 0 is analytic. It's not, and similarly for here, it is the value of here will be 2 over 1 minus x is equal to 0, that will be 2. So both 0 and 2 are analytic, which means that these functions are continuous, or they exist at the value of x is equal to 0. So the functions which do not exist, they may have something like divided by 0, or infinity over infinity, or infinity over 0, something like this. So those undetermined form we will obtain. So this is the case in this equation. Okay. In this case, if we take x is, if you put the value of x is equal to 0, so both of these coefficients of y prime and y will be undetermined. So we say them, these are the singular points of these equations in this case. So for this singular case, we cannot directly apply this power series solution. So for example, if you know that for these two types of equations, so for this equation and for this equation, we can apply this power series in which we have m is equal to 0 to infinity, am x power m as the general solution. Okay, so for these two types of equation. However, for this equation in which the y prime and y, the coefficients of y prime and y are not analytic, we cannot apply this power series. Okay, we cannot apply this power series. So for this, we have this Frobenius method. Okay, so Frobenius method says that if we have this kind of situation in which any of these two coefficients of y prime and y are not analytic, then we can find its solution by this series. So this series is similar to the power series, but with an addition of x to the power r, and then m is equal to 0 to infinity am x power m. Okay. So in this case, we will apply this type of substitution, or we will use this type of series to find the solution. Okay. So I think now it is clear that why we will be using the Frobenius method. So for the singular case, or where these functions are not analytic, we will be using the Frobenius method. And for analytic functions, we will be using the power series method. So this normal power series. So anyway, both of these power series are not very much different from each other. This one and that one. The way of calculations is also same. So we can, I can try to illustrate it with the help of some examples as well. So anyway, so this is the power series. So if I will expand it, so it will be like x power r, and then it will be a naught plus a1 x plus a2 x square, and then so on. Okay, so this series will go on like this. But remember that in this case, we will not take a naught is equal to 0. So a naught, so this is the condition for this Frobenius method. The value of a naught we cannot take equal to 0. Okay, we cannot take equal to 0. So the Frobenius method says that if we apply this substitution in the form of this power series involving x power r, we can get at least one solution, because we need two solutions, because this is the second order differential equation. We need two solutions, but by this method we can get at least one solution. Okay, we can get two solutions as well, but a minimum we can get one solution. So if we have one solution, the other solution we can find by methods such as the reduction of the order method. Okay. So is it clear? So what is the difference between the Frobenius method and the normal power series method? So yes.
So the difference is that when we use the Frobenius method, we suggest that it is like finite function. We like it has a finite form. Uh,
No. Uh, we use Frobenius method for these type of equations. Okay, for these,
for the ones, okay,
so
for the ones that
where
make
yes,
where the function goes to the like to
infinity. Yeah. So
infinity.
for
Yeah, that
example,
diverges.
if we take x, yeah, it will diverge. You can say diverge. So for example, if we take the value of x is equal to 0 over here, then it will be undefined. Okay.
Um, sorry, sorry. So when we want to use the Frobenius method, should we like justify using it by making a like convergence divergence test, or we can just use it as just as we see it pleasing, like
Yeah.
like
So when
should we
no, we
justify?
the convergence and divergence test you have to apply on the series. Okay. So since we are
Uh-huh.
that we will not that you will not need to do. You will have the differential equation. So on the differential equation, you don't have to apply these convergence and divergence methods, because convergence and divergence of the series, I actually did not discuss about it. That is part of the calculus course. But anyway, since we are not starting with the with those series which are diverging, we are always using the in converging series. So for
Uh-huh.
purpose, we can use it, but here, no, there is no need. We only
I
need
mean, yeah, okay.
to check whether these functions are analytic or not. Yeah, these two
Oh, okay, okay.
ex, these functions are analytic or not functions. Hmm. Okay, so so in order to apply this Frobenius method, so we have to use some substitutions for y double prime and y prime. So in this case, like for the for this traditional power series, so we can use the substitution. So for this, we can need to take the derivative of this. So y prime of x then will become become uh, so in this case, since well, we can take the derivative, but we can also simplify it like this. Like we can take x to the power r inside, so it will be am x to the power m plus r. Okay, so we will be taking the derivative of this series. So for example, this will be um, m plus r. Should be, I should have the sigma notation over here. First, we have to take the sigma notation. So m is equal to 0 to infinity, and therefore there will be m plus r. So the power will come as the coefficient. So it will be am x to the power m plus r minus 1. Okay, so it will be a y prime. Then we will have y double prime of x. It will be m is equal to 0 to infinity. Okay, so now this power will also come over here. So it will be m plus r into m plus r minus 1 am x power m plus r minus 1. Okay, you can expand this series for a few terms, this one and this one, but I will skip it for now because I don't have enough time to cover to write all the steps of the calculation. So I will only write the steps for the final.
Can
So
I ask,
yes,
is it -1 or -2 double
yeah,
prime?
this will be -1, -2.
Okay, thank you.
Correct. Okay. So now what you can do, now we can put these notations into this, for example, if we take any equation as an example, yeah. So into this, for example, into this general equation. So for example, if we want to use these values, so for example, y of x, this one, and this one, and this one. So we have now the general equation like this. Yeah, this is the general equation. So general equation we can get by, it will be easier if we multiply it by throughout by x square. So it will be x square y double prime plus b of x y prime plus c of x, yes, c of x and b of x x y prime, okay, and then c of x y is equal to 0. Okay, this is the equation. So here we have these bx and cx functions. So bx and cx functions will be analytic. Okay, they will be analytic functions. So therefore they will have their own power series. So for example, for bx we can represent it like m is equal to 0 to infinity bm x power m, or for cx we can represent it by its power series, m is equal to 0 to infinity cm x power m. So now in this equation we will input the values. So x square, okay, and then the value of the y prime. So it will be m is equal to 0 to infinity m plus m plus r minus 1 m am and into x power m plus r minus 2. Okay, and then for bx you will have this series m is equal to 0 to infinity and bm x power m and then for that is multiplied by x. So I will put x over here, and then another sigma notation that is for y prime. M is equal to 0 to infinity. So it will be m plus r into am x power m plus r minus 1. Okay, so this will be this. And then for cx, it will be m is equal to 0 to infinity cm x power m, and then plus sigma m is equal to 0 to infinity. This is actually y. So it will be x power r. I can take it inside. So it will be am x power m plus r. Okay. So, and then that is equal to 0. So actually now there is a some algebraic work is involved. So for example, maybe you will have to multiply these two series, okay, and then collect the terms together, and then you have to multiply these two series and collect the terms together. I think this one should be multiplied over here. Collect the two series and multiply the terms together. In any case, in the end, you will get a relationship, okay, by the by simplifications. So because I'm skipping those steps, by simplifications, you will get the result like this: r into r minus 1 plus r b naught plus c naught, and then that will be equal to 0. Okay, so you will get this equation. This equation you will get by equating the lowest power of x in this by equating the lowest power of x into this equation on both sides. So you will get this equation for the value of r. Remember that r was the only difference between the traditional method and the Frobenius method. So in the r is an additional term in this Frobenius method. So by this equation, we can determine the value of r. Okay. So as a theory, then we will have three cases. Okay. First will be the case 1, because if you see that this equation is a quadratic equation. So for a quadratic case, we can have various combinations. So for example, we can have the real roots, and we can have also the double roots, and we can have the complex roots as well. Here we will not be talking about the complex case over here. So we will be taking the two cases. So in two cases, we will in first two in all the three cases, we will be considering the real roots. So for example, in this from this equation, we can find two roots, r1 and r2. So r1 and r2 may be different, and r1 and r2 may be same as well. So the case 1 says that r1 and r2 are real and distinct, but they are not, but they do not differ by an integer. Okay, do not differ by integer. Okay, so what is the meaning? For example, if r1 is 3, then r2 may be 1 by 2 or any other value. Okay, so r1 and r2 are different from each other, but they are not different by an integer value. They are different by some non-integer value. 3 minus 1 by 2 is 5 by 2. Okay, so this is case 1. Okay, there will be a case 3 as well, in which R1 and R2 will be different, but they will be different by an integer value. So in this case, if R1 is 3, then R2 will be, say, like 1 or 2, something like this. So the difference of 3 and 1 and 3 and 2 is always an integer. So we will take the case 3 later on. So in this case, the theory says that if this is the case, if we find two solutions and of R1 and R2, so we will find the we can write the two solutions of the equations as the sum of the as two series. So first series will be x power R1 into a naught plus a1x plus a2 x square and so on. So same like a power series, but with the multiplication of x to the power R1. And the second solution will be obtained. Second solution will be also a power series, which will be x power R2 into some other coefficients, okay? A naught plus a naught x plus sorry, a naught x plus a1 x, okay, and plus a2 x square and so on, okay. So in any case, it is important to find the first solution, and then the second solution can be found conveniently by the reduction of the order method, okay. So this is the case 1. In case 2, R1 will be equal to R2. So both will be same. So that means we can say that both are equal to R. So this means that the double root, okay, double root. So in this double root case, the solution will be y1 is equal to, y1 will be equal to same as before, x power r into a naught plus a1 x plus a2 x square and so on. However, y2 solution will involve a term which will be log of x. Okay, so y2 solution will be equal to y1 of x, okay, times log of x, and plus possibly other terms. So it will be a1 of x plus a2 of x square and plus a3 of x cubed and so on. Okay. Remember that in the second term, there will not be a term without x. All the terms will be with x, because the term with x without x has been taken care of in the first part. Anyway, this is just for the remembrance only. So in this case, you also have to mention that since the log x is involved, so we cannot take the values of x which are less than 0. So the value of x will be always, the value of x will be greater than 0 in this case. So this is the case 2. Okay, case 3. Please note that we are not going into the derivation of these theoretical means. So I am just explaining the method. So if we go into the derivation, then it will be too long, and then I don't think we can cover it in this in the time which we have. Okay, case 3. Case 3 is also same as similar to case 1. R1 and R2 are different by an integer. So for example, if R1 is 3, then R2 may be 1, okay, or R2 may be 2. So their difference is an integer. So in this case, the solution will be given, maybe I can write for case 3 here, okay. Case 3. The solutions, two solutions will be y1 of x will be equal to same as before, x power r1 into a naught plus a1 x plus a2 x square and so on. However, y2 will be equal to k times y1 of x log of x plus x power r2 a naught plus a1 of x, capital A naught plus a1 of x plus a2 of x square and so on. Anyway, so here the difference between the case 2 and case 3 is that in case 2 it is essential to have a log x term in the second solution. However, in case 3 it is not essential. In case 3, depending on the value of k, which may be 0 as well, this second solution may not have the log x term, because if the value of k is 0, so this term will vanish. So there will be not log x term in this case 3. So case 3 may have a log x in the second solution, but case 2 will always have a log of x in the second solution. Okay, so let's see one example. The application of such this example. So for example, that's solution is equation is x into x minus 1 y double prime plus 3 x minus 1 y prime and plus y is equal to 0. So this is an equation. So you can see that these functions, for example, function over here and function over here with the y prime and y, they both are analytic. So for example, at x is equal to 0, the value is minus 1, no problem. For x is equal to 0, the value is always 1, so no problem. So both of the functions are analytic. However, when we write it in the standard form, 3x minus 1 over x into x minus 1 y prime plus 1 over x into x minus 1 plus 1 over x into x minus 1 y is equal to 0. We will have this form. So in this case, if we put x is equal to 0, so there will be 0 in the denominator. So these functions will not be analytic. So therefore, we need to apply the Frobenius equation, Frobenius method into this equation. Okay. So for the application of the Frobenius method, so we will use this form of the equation. So for example, in this case, the first, let me write for the Frobenius, the summation notation. So for the Frobenius method, the summation notation is for y of x, it is equal to m is equal to 0 to infinity, am x power m plus r. Okay, and for y prime of x, it will be 0 to infinity, m plus r, am x power m plus r minus 1. And then for y double prime of x, it is m is equal to 0 to infinity, m plus r into m plus r minus 1, am x power m plus r minus 2. Okay, so we will have this. So here, if you see that in this equation, so y prime is being multiplied by x square and then also by x. So we first multiply it by x square. So if we multiply this by x square, so it will be -2 will cancel out. Okay, so we will be left with m is equal to 0 to infinity m plus r into m plus r minus 1 am x power m plus r, m plus r. So we will be left with this. And then it is minus x. So if we multiply it by minus x to the power 1, so it will be m is equal to 0 to infinity m plus r into m plus r minus 1 am x power m plus r minus 1. Okay, it will remain like this. So this y prime term is being multiplied by 3x and also by -1. So for 3x, it will be, I can put like 3 outside, and then m is equal to 0 to infinity. So it is being multiplied by this. So since it is multiplied by x, so here it was x power -1. So 1 will cancel out. So it will be m plus r into am x power m plus r. Okay, and then for -1, so it will be this minus of this term. So minus m is equal to 0 to infinity m plus r am, and then x power m plus r minus 1. Okay, and the last term is plus y. So plus y is simply this term. M is equal to 0, infinity, am, x power m plus r. So after we have set up this equation, we also now have a lot of work to do. But one thing which we can do is, in this case, we can determine the value of r by equating the powers of the lowest term. So the lowest term will be x to the power r minus 1. So for example, if we put m is equal to 0 over here into this, so this will be let me erase it. This will be x power r, okay? And in the next term, it will be x power, because m is, if we put m is equal to 0 over here, it will be x power r minus 1. So the lowest power in these 5 terms will, for x, will be x power r minus 1. So we can equate the coefficients of these two terms on both sides, and then we will get an equation which is called, which will be this equation, minus r into r minus 1 a naught x power r minus 1 minus r a naught x power r minus 1 is equal to 0. Okay, so you will get it. I think you have to do the verification for getting whether you can get it or not. So in this case, if you will simplify it, so it will be r square plus r minus r is equal to 0. And in this way, we will get a double root r square is equal to 0. So we will get a double root r is equal to 0. So this will be a double root. So in this case, this will be a double root, and then that will be considered as a case 2 in this case. Can we continue 10 more minutes? Okay, so that we can complete it. Okay, in order to
yeah,
this,
yes.
yeah,
Okay.
we can continue 10 more minutes. Okay, because we also lost some time early. Okay, so one thing is that, so first step is to determine the value of r. One thing I forgot to mention about is that this type of equation is called as the indicial equation. Okay, indicial, it has a special name, indicial equation. Okay, so we get an initial equation. For the indicial equation, we get the value of r. Okay. Next is also step is that you have to do the manipulations and algebraic calculations to equate the terms on the both sides. And the end result will be that because some of the terms will have am and some of the terms will become am plus 1. Okay, so in this case you will have a recursion relationship. Okay, recursion relation. Okay, recursion relation. Remember that if you do the equation, if you equate the coefficients on both sides of this equation, so you get a recursion relation. And I will not go into the details of these steps, but the recursion relation in this case you will get will be like this: am plus 1 will be equal to am. Okay, where m will start from 0 to 1 to 2. So this is a very simple recursion relationship which you will get from here. So you can see that there are so many terms over here, but all of these terms will actually cancel out, and then you will get a very simple recursion relationship for this type of equation. So what it will mean? It will mean that if we take the value of m is equal to 0, so a1 will be equal to a0, okay, and then a2 will be equal to a1, which means that it will be equal to a naught. So which means that all of those coefficients will be equal to a naught. All the coefficients of the equations will be equal to a naught. So our solution is what? What was our solution? Solution was this. So for example, the first solution in this first case was, it was equal to x to the power r. What is x to the power r? X to the power r is 0. R is 0. Okay. In this case, r is 0 into a naught. A naught will be the arbitrary constant, and then it is equal to a naught x plus a1 x, okay, square, and then so on. So we can write this equation as m is equal to 0 to infinity, that is equal to x to the power m. It is simply the summation of the x to the power m. And we know that this type of a power series is the power series for a geometric series, 1 over 1 minus x. Okay, this is the power series for a geometric series, which is equal to 1 over 1 minus x, where the absolute value of x is less than 1. Okay, that means the value of x should be less than, only then this series will converge. Okay, so we get one solution as 1 over 1 minus x. Okay, so we can get the other solution by the reduction of order formula. If you remember that long time ago, we developed the method for the reduction of order at the start of the second order differential equations. And over there, at the end of the topic, there was a formula for the second solution. So for example, if we know the first solution as y1.
Using the Wronskian method?
No, it's much before the Wronskian method.
Okay.
I will remind you. Okay, so y2. So if we have the first solution, we already have found. The second solution we can find by this method. Okay, by the multiplication of u. But how you determine u? In this case, y1 we know, and then from y1 we can find y2 by multiplying it by u. But we need to find the u. U is equal to the integral of capital U. Okay, and whereas this capital U is equal to the 1 over y1 square. That means this into e power p dx. Okay, p dx. Okay, this is the solution. But what? Yeah, maybe you remember now. So, so what is P? P is in this case is this 3x minus 1 over P is the coefficient of y prime. 3x minus 1 over x O into x minus 1. So P is equal to, P is equal to 3x, sorry, it is minus, no, it is P is equal to, sorry, 3, let me see. So P is equal to 3x minus 1 over x into x minus 1. 3x minus 1 over x into x minus 1. Okay. So if you take the integral of that, and then you will find that the value, the u will be equal to, u will be equal to 1 over x. Okay. And then finally, you will find small u will be equal to log of x. Okay. Small u will be equal to log of x, and then y2 you will find as u times y1. So log of x times, and what was y1? Y1 was, which we find in the previous case, y1 was 1 over 1 minus x. Okay, so y1 was 1 over 1 minus x. So the second solution will be 1 over 1 minus x in this case. Okay, so you will use this formula to find the u, and then from capital U, you will find small u by the integration, and then just input into this equation y2 is equal to u y1, then you will find the second solution. So in this way, we have solved this equation, which is called as the hypergeometric equation, by using the Frobenius method, and then we found the second solution by the reduction of order formula. Actually, I have skipped several algebraic steps in over here. So, for example, here we have to actually take the. We have to also take the partial fraction as well, and then you will be able to find the solution. Okay, so in this case, then now you can find the second solution by the reduction of order, method, along with the Frobenius method. Yeah. Okay, so I will upload one more example in the recorded video later on, and then later on, in the next lecture, we will cover the other method, which is called as the Bessel's equation, and then that topic will complete. Okay, so do you have any questions?
No.
Okay, then that's all for today. I shall see you on next coming Wednesday with another method for this topic. That's all for today. Bye-bye.
Goodbye.
Thank you.
Bye-bye.
Goodbye.
Bye.
Bye-bye.
Goodbye.
Bye.